Yes.
Yeah, thank you. Thank you for so much nice introduction, and I really honored to many people, including great committee members that can spare amongst the busy times and challenging year. And today I'd like to share some part of my PhD journey, which is titled here as Exploring Meditation for Guidance and Technology. It's probably one of the most fascinating piece of the part in my PhD. So I'd like to go for next 45 to 50 minutes about this topic, which I hope it will be enjoyable and informative. So before going to a little details, I'd like to start with like rather deep, bigger pictures or motivations or excitement that really drive me, not only me, but probably many, many people in the field, which is about interfacing with the human body, and which is actually really emergingly interesting and challenging topic as we see a large number of or rapid number of artificial materials, fine materials, and the machineries, even complex forms, are start to coming on or inside the human body in different places, from eye to brain and even guts and heart, etc. So it's under the vision of some kind of board like the Internet of Things and Human of Things. So people talk about a lot of things, but somehow it's like we are trying to start to merge artificial man-made things to our bodies in different places for different functionalities. But along this big stream of the research and development and innovations, the issue is always kind of coming up because the biological system, our body, and the artificial system that what we made as a human is different thing in a variety of different ways, as the human body is a naturally derived living materials. And they are pretty much have a high water contents, like the 70% of our bodies are water. And they're typically soft materials, although exception of the bones or nails. While in contrast, the artificial systems are generally synthetically made, is dry material, low waters, and typically stiff material, which are very, very, very kind of a low level of dissimilarity, but we can see a lot more dissimilarity in detailed look. But the issue is that they are so much different in terms of their property and a working mechanism that operate. So when we try to merge these artificial things to our body, both inside and outside, these differences can cause a lot of rejection and trouble, problems, or challenges. So how to allow these two different worlds are merging together each other in intimate manner and does not cause trouble and do the job we wanted for long term, interfacing very nicely. One of the biggest ongoing challenges in the broad range of field, not only the field that I'm working on, but field that other people are working on, a variety of different sectors of is a relatively big stream of the movement. And among various ways to talk about these challenges as a material scientist, engineer, and also mechanical engineer, one class of a material they called hydrogels or jellos or tofus, if you're more familiar with the kitchen items, are really fascinating class of material, which is first starting with the definition, these hydrogels are polymer network infiltrated with a large amount of water, or if I go more a little descriptively, is a nanoscale fishnet that's soaked with a large amount of water. It's really fascinating class of material in terms of bridging this interface between these two different worlds. It's partly because this material, the hydrogels, are having very unique features such as high water contents and mechanical softness, and while it can still be robust and biocompatibility and functionality, even allowing the tissues and cells that is like growing within or around it, and it has a lot of water that allowing the ion-based electrical transmission is still possible. So it has a lot of similarity to the biological tissues in our body, while as engineering material, it can be designed and tuned and optimized for the desired properties and functionalities. So it's kind of something that presiding in between these two different worlds. So it can be a very much ideal material choice to interface these two different things that when we want to make it kind of intimately acting each other. And it's actually not surprising because when we think a little further, our bodies or animals' bodies are largely composed of a protein-based hydrogels, like a hybrid with some rigid components. So considering the fact that our body itself is a kind of a hydrogel, like a meat or flesh, if you want to call, it's not a surprising to see the hydrogel kind of really interesting class of material that have a potential of doing a nice job in terms of interfacing these two different worlds. But despite a great advances in the last several decades in a variety of different perspectives and aspects of these technologies, the hydrogel technologies as an ideal interface between these two worlds. still face a lot of significant challenges and oftentimes limiting their true adoption in a practical application, even especially beyond the laboratories and research papers. So, but as a researcher or inventor who always seeking for something exciting, new things, the challenges always means the opportunities. So, but there are so many problems and challenges. I had to choose what I want to solve mostly and what I want to contribute. So I choose three questions about these challenges, which becomes the question that I explored in my PhDs. The first question I asked is how to integrate. In my opinion, is probably one of the most fundamental questions one can ask, because integration or combining dissimilar materials and make sure they are stable and robustly held together do the function is probably one of the basic requirements that anything that can combine based on more than two materials. So this was the first question I asked. And second is how to communicate, which is becoming more and more important as we are trying to put something that are bidirectional communication between the artificial world and our bodies, but oftentimes electronically. And the third is how to fabricate, because as engineering, making or generating some raw materials into a desired shape and structures, especially small scale, is really critical part of the process because it really or essentially required to generate something that do the function. But the fabrication becomes a bit more challenging a question for a soft and the wet material like the hydrogels or biological tissues, etc. So for each questions, I answered like each, for example, how to integrate. I studied based on wet adhesion biological technologies. For communication, conducted hydrogels and hydrogen bioelectronics. And for fabrication, I studied 3D printing of sub-functional materials. But sadly, due to the time limit, I would like to focus only on a first question with two parts. First part is the wet adhesion, and second part is biological technology, a little more application focused. While I may not be able to cover the other two, which is around the half of my PhD study, but I'll be happy to discuss after defense personally if you're interested. So let me first start with the wet adhesion, about the design principles and implementation of various wet adhesion things. So before start, I need to define what is wet adhesion. So this is my personal definition, so it's not kind of dictionary thing. So wet adhesion, in my opinion, is interface or integration of a highly water-containing or wet materials such as hydrogels and biological tissues. So in my opinion, this, again, the wet adhesion is probably one of the most basic requirements that something would work or desired functionality, because when we are trying to use hydrogels or biological tissues, any wet material in combination with the other dissimilar material, if their assembly just to become very weak and unreliable and fail breaking down, that's probably the easiest way something is not working, something is not kind of properly doing the job we intended. So making sure assembly of a dissimilar material with a wet material such as hydrogen-filled biological tissue is a basic requirement to do anything that meaningful, especially in a harsh environment or dynamic environment like the biological tissues. And wet adhesion itself is quite much challenging than dry adhesion that we see everyday life, like our smartphone has tons of adhesives and like the scotch tape and sticky note that on the table. It's doing a great job, but when it's something become wet and watery and even living like a biological tissue, the question of adhesion becomes far more challenging. But among many, many challenges, I choose three key challenges that I'm really excited about in elevating complexity and the challenging nature, starting from the weak and brittle adhesion, because it obviously needs to be strong and robust. And second is a slow adhesion problem, which is more practical issue I would like to discuss a little later. And third is a fouling resistance of the problem, which is more practical because our daily, in practice and reality, many surfaces are simply not clean. And for each, I try to solve the challenges based on each aspect of the wet adhesion that I actually try to solve. And I want to start with the weak and brittle adhesion and how I solved. So the tough wet adhesion that I call in a little more detailed manner, robust wet adhesion with the high toughness and the strength, is actually not really a surprising thing. Nature is very common because our body and animal is basically a combination of soft wet materials and hydrogel like the fleshes or muscles in combination with something that is other materials such as bones and shells. And in terms of assembly, when we think about ourselves or animals assembly, if this adjoinment between this wet material and other things are weak and brittle, they may simply challenging their survival against the harsh environment or some against the predators. So it's not surprising that in nature, this tough addition is a kind of common for their own good. For example, the interface or toughness or work addition or addition energy as people want to pour in their own field is pretty high for the tendon and bone interface in our bodies, like around 800 joule per meter square. Even the muscle shells on the seashore rocks and even our skins, the epidermis and dermis assembly shows pretty high values such as 100 joule per meter square, etc. And as of this is pretty common in nature and is important, it's not surprising that I could find lots of literatures when I started to look at this problem that people have studied a lot. But when I studied the literature a little more deeply, the previous research approaches when I started looking at this problem was mostly focusing on interfacial chemistry of addition, such as muscle-inspired addition, was a remarkable work that is pioneered by Professor Herbert Wade and Messerschmitt, etc. But when I take a look at this a little deeper as a whole picture of the addition, this interfacial chemistry that about forming the interfacial anchorage is really nice. But when I take a look at the ordinary hydrogels addition by adopting this method, it just breaks down much easier because the interface is actually still there, but the bulk mature break out first. So therefore, it cohesively fails. So the bulk failure of the material above it is basically limiting the how much of the fracture toughness we could get is around the order of 1 to 100 joule per meter square. So it kind of become very obvious question to me that being curious about if the interface is still there, but it's break up above it, what's the role of the bulk hydrogels in wet addition? And around the moment when I first joined this lab, this group, the field of tough hydrogels, the making of hydrogels that are kind of tough and mechanically robust as a biological tissues are generally pretty robust materials, pretty flourishing at that moment. So when the tough wet addition is actually existing in the nature, and they do have made out of those tough hydrogels, the obvious question that I can ask and try is maybe the tough wet addition is not only requiring the nice interfacial formation by nice chemistries, but also requires a pretty nice material above it. So what about like tough hydrogels with a high fracture toughness? So what I did simply is I just took up the tough hydrogels in the lab and get some chemical thing that I from the literature and just tried it. And it was a remarkably exciting experiments that I did. It was so tough. It's so robust. You can see from the video. Its number is really high, and I could not even separate myself using my own hand. And the glass substrate break down multiple times during this. So I somehow made a tough wet addition by just combining this tough materials with this interface and anchorage. So it was a very exciting moment for us to observe this first. And then our teams are like boil down these observations multiple times into a little more general design principles of a tough wet addition that called a synergistic combination of a strong interface linkages that about interface, plus the mechanical dissipation and bulk material. The material should be pretty robust and dissipative material. So therefore, the tough wet addition is requiring a bulk and the interface synergy, as you can see as summarized in the schematics. And this is pretty conceptual proposal. So, but still, it can be implemented in a variety of different hydrogels and a substrate by using different chemistries, some of which I learned from the literature, and some of them I invented myself, especially for the stretchable elastomers. And remarkably, we could achieve the interfacial toughness gamma here as over 1,000 joule per meter square, which is exceeding the that of the bone and tendon. It was a fascinating value at that moment because it was the first time we could achieve this value on a wet material such as hydrogels. But it's not anymore a highest value because people did such a great job of picking up the numbers again and again as or the fields are growing. And I could do this in a variety of different materials like glasses, metals, ceramics, and even structural elastomers. And retrospectively, we find these initial concepts and tools are really probably offered some nice play tools for the emergence of the interesting field called robust hydrogel solid hybrid. And we could see that it becomes really flourishing and vibrant field now. So we are pretty happy with it. And as a mechanical engineer, we wanted to understand this in a little more mechanistic way. So we try to model these two basic components of the tough wet addition, the interface and the bulk. And models like, for example, the interface can be modeled into here as, for example, the triangular cohesive zone model, which is one of the simplest way to model how much of the energy is needed to separate interface between two materials. And the dissipation in the Berkeley materials being modeled in Lewis effect, which is originally developed to capture the dissipative behavior of a particle containing a rubber material, such as car tires. So these models can be implemented in numerical software for the finite element simulation by collaborating with the numerical experts in our group at the moment. And we could see that the interface's contribution is just measured exactly the same value. The gamma zero is just simply gamma zero if we do not have a dissipative effect on the material. But once we start to model the dissipative effect in the bulk material, the actually measured values are like synergistically increased a lot. So which is kind of validating what we conceptually proposed and experimentally observed. And we take a look at a little further into these two key components that are controlling the toughness diffusion, which is intrinsic interface toughness gamma zero and dissipation energy. And each of it actually can be controlled parameter for the interface. We can control as the strength of the interface linkages or their densities. For the dissipation itself, we can control as a material property itself of the material that we use, or it can be also thickness-wise controlled because thickness is kind of bounding how much of the maximum dissipation can happen, because for too thin material, it is bounded by the thickness of the material. So we can express in a way that the total interface energy toughness we measure is a combination of this interface's contribution and the work's contribution, which are affected by both a material property and their geometric factors. And we have to test it experimentally, and the trends are captured in finite element simulation as well. So it's kind of not only the conceptual proposal, but it also can be a more like a quantitatively discussable or like a useful design parameters and design guidelines when we want to make something tough when it comes to the weather diffusion. So this was the first work that I did in this group and was very fascinated. And it takes several years to touch the second problem, the slow diffusion for me, like it takes around 3 to 4 years to get to the second problem, because it was more practical problem in my opinion. So, but it was still very fascinating. So going for the slow diffusion problem, as an engineer, I always think that to solve the problem, I need to understand what is the source of the problem. So I take a look at a variety of different examples of wet adhesion, especially tissue adhesives that are commercially available and are very heavily studied, because the biological tissues are always wet materials. So the tissue adhesives are automatically talking about wet adhesion. And I find that there are oftentimes, most of the times, is actually in the form of the viscous liquid itself, or a viscous liquid applied between some other hydrogels and like target tissues. And all of them are actually sharing a single mechanism that's called the diffusion cross-linking process, in which this liquid is actually should diffuse through the tissue surface and form the interpenetrated crossing for solidification or chemical crossing to make the adhesion formed on the wet surface. And the fact that at the moment, I actually kind of realized that this wet material, especially tissues that operating in a wet environment, for example, inside body, is a hydrophilic material with a high water content. So it is inevitably always have a certain like layers of water. In here, I call it as interfacial water is around 50 to 100 micrometer thickness when I measure it in this microscope. So it seems like it's this presence of interfacial water, which is inevitable most of the time, except a few dry cases. And the fact that they are relying on a diffusion and cross-linking process across the board is causing the problem of slow adhesion first. Diffusion is not an instant process. It takes time because you need to cross a certain distance to reach the destination, the surface of the wet material. While this presence of interfacial water is really increasing the distance this material should travel through, so it really makes it slower and cannot be instant. Second, this liquid form of the glues can be diluted and mixed with interfacial water, so it actually can further slow down the reaction and or make it unstable or patchy. So this presence of interfacial water in combination with this particular mechanism of a diffusion and cross-linking process is really causing the issue of the slow adhesion. So I realized that whatever chemistry I may change in this viscous liquid may not probably fundamentally solve this issue, because it's really, there is a problem that are causing all the issues. So I actually had to go for a little new perspective. So what's if the interfacial water is the source of the problem? I just remove it. And the answer was yes. Because so we actually come up with a pretty radical approach that we later named as a dry crossing mechanism. So instead of relying on a diffusion of the liquid, we started from a dry biodiesel material that instead of doing diffusion, it just rapidly absorbs and removes the water from the wet tissue surface or wet surfaces. And following subsequently, we can actually form the physical and chemical crossing to form the fast flow diffusion. So it's actually how it works like this. So it's starting from a dry material. So instead of diffusing something, it just suck up the water from the surface. So removing the interfacial water makes the tissue exposed and then form the very fast physical crossing, such as hydrogen bond, followed by a faster crossing, covalent crossing for the more stabilizing the interfaces. So it was really nice conceptual thing that I could first experimentally implement to work out. But again, as a mechanical engineer, and especially this is pretty interesting in terms of mechanical perspective, we wanted to understand this better because now we are not using a liquid, and now we are not using a hydrogel that swells. It is starting from a dry material that absorbs the interfacial water and perform the adhesion. So it's actually not only swelling, but it's actually first to go the hydration of the dry material, and then subsequently it swells, and then it equilibrates in a wet environment. So it's a hydration and swelling coupled situation, which is very interesting, which is different from just simple swelling. So we wanted to take a look at this process itself a little bit deeper, from which we hope that we actually further understand why it can be faster and whether we can further understand in a kind of model-like way to have a design guideline, not only a conceptual proposal as a mechanism. So we devised some interesting experiments to understand the hydration process. Basically, we have some nice fluorescent dyes, and when the whole layers are hydrated, it light up. So we kind of fitted this experimental data with the Fickian models, and we could come up with a one parameter, which is KH, your hydration coefficient. It's basically the diffusion coefficient of a water molecule during the drying process. And with that, we modeled, we formed a model with the collaboration of previous member in the group that this is the expected height changes of the dry adhesive in contact with the interfacial water. And we check it with experimentally fits very well. So this process of a coupled hydration swelling is actually really capturing very well what exactly happening in this dry adhesive. And from which we actually can dig further into that when we think about a time scale of the actions. When we call the T water as time required to dry the interfacial water by starting from the dry adhesive, it may not be very different from the time diffusing the monomers, assuming there is no interfacial water. But the monomers are pretty much not commonly used, especially the applications, because they are toxic. So oftentimes people use a little viscous liquid that's based on polymers. And the polymers diffusivity is actually much lower than the monomer. And if they are a semi-dilute solution, it may follow the Rose model. If it's dilute, it may follow Zim model. And that, the time scale of this viscous solution would be much longer than that of a monomer. Plus, because they cannot or do not remove the interfacial water, they have extra distance to travel through to reach out the surface of the wet material. So therefore, this is probably a little more detailed explanation of why the dry cross-linking mechanism that we are trying to use is much faster than previously used the diffusion cross-linking processes. And also because now we have a little more established understanding of this, is not only conceptual proposal in terms of mechanism, we can use that as a design guideline of how much of a thickness, depending on the material property of the dry adhesive we're going to use, be necessary to remove a certain thickness or amount of interfacial water in the situation. So it was pretty exciting. And with these two things are being done, I was so encouraged. So I now really understand well this wet adhesion. So probably I may have a chance of absorbing so difficult a fouling resistant wet adhesion with these two things. I actually now understand better. And why this is so challenging, because the wet adhesion alone is already pretty much more challenging than dry adhesion because of the many issues like wet material. But when something is not clean on the surface, and which is more practically common situation, and say it's the surface is contaminated with the various foulants, which is probably blood is most common in biological realm or mucus. This situation make this challenging nature of weather condition far more exacerbated because this foulant is a contaminating, diluting, and deactivating adhesive, and blood is full of cells that can act very nicely as like they are tissue surface. So it can become useless before actually they are doing the job as adhesion on the wet surface. And furthermore, this foulant, especially blood kind of thing, is not a static foulant that's residing on the surface. It's sometimes actively coming out with a certain pressure. So it can impose a much more challenging environment to deal with this wet adhesion, and which is very common in the clinical settings like hemorrhages, etc. So in my opinion, this is pretty much harder situation for wet adhesion, but because it is common in important applications such as clinical and biomedical situation, it is very important to solve these problems. And again, we need a new perspective because there is not very good understanding out there. And I asked a very simple question like, if foulant cause trouble, why not clean the surface? Which is very simple question. But the issue at this time is how. I have no idea how I can do this simple statement. But around 2 years ago, when I attended a boarding conference near Boston, I had a chance to learn about an extraordinarily interesting marine organism called barnacles. And these barnacles have amazing ability of forming such a robust adhesion, not only a rock, but on a super contaminated man-made rusted surfaces, and even mucus-covered animal surfaces, animal skins, was remarkable. And why they could do that based on the researchers who are studying their data is because their glues of these barnacles have a very special composition. Not only they have adhesive proteins that are acting as like adhesive, but they are suspended in a lipid or oil-rich matrix. And this matrix is acting first to clean the foulant from the surface, basically terraforming the dirty surface to better prepare for this adhesive proteins being crossing and form adhesion. So it's basically really nice cleaning process happening just based on their nice composition. But I'm not a biochemist, so I didn't kind of try to even mimic this complex peptide, etc. So instead of that, as a mechanical engineer, I wanted to get inspired by this beautiful process, which I a little more generically named as a repel cross-linking processes, in which the hydrophobic matrix can repel the foulant and clean up the surface, and therefore allowing the suspended adhesive material, in here microparticles, but it can be anything in forms, interacting with the exposed and clean the wet surfaces to form something nice adhesion. So not without interference of the foulant afterward. So it's a kind of a pretty inspired mechanism, but I think it was a kind of clever that I was very happy to do this and check it out is working thanks to the small barnacles. But again, this is just a conceptual proposal. Even though it works experimentally, we need to understand why it works. So as a mechanistically speaking, we need to take a look at why it is working. So in this case, to take a look at in a little energistic landscape of what's going on here. So if we take a look at the situation a little like a configuration ones, there can be three configurations. Configuration is a starting point. We applied a adhesive that suspended in a hydrophobic matrix on the foulant-covered surface, like here is tissue. And this is the initial situation. A second configuration might be a failure. So the foulant is basically wetted, completely wetted the adhesive, inactivating or messing it up. And this hydrophobic protective matrix is separated out. So this is failure because, and then in this situation, nothing would happen as we wish. And the third configuration is the success cases. All the foulants are successfully removed from the surface and the suspended by this and now can freely contact with the target tissue surface or wet surfaces without being interfered by the foulant. So to make this proposed repel cross-linking mechanism to work, we need the configuration 1 is preferred over configuration 2, which means they should have a lower energy state. And configuration 3 should be preferred over configuration 1, which means they should have a lower energy state, which means these two energy inequalities on the left side of the slide should be polar. And because we know these expressions and these values are experimentally measurable values, so we put some real numbers. Hydrophobic matrix, which is medical grade silicone oil, which is very commonly used hydrophobic materials in the clinical and biomedical world. And for foulant blood, the blood is the worst foulant we can imagine. So then we calculated, and both inequalities actually force very well. So which means it is not only a body-inspired conceptual mechanism, but it actually works because people prefer to work. So it was very, very nice to see in this way. And I experimentally validated, and only when we have the hydrophobic matrix suspending the bioadhesives is working nicely against the, like, for example, this is a tissue that's soaked and submerged in the bath of the blood. While if we only have the adhesive or hydrophobic matrix alone, or the hydrophilic matrix, which is not capable of nicely repelling the foulant because it's easy to mix up each other, is not generating a nice adhesion because they are being easily fouled or it doesn't simply work out. So it was a kind of one of the most recent thing. And with that, I wanted to explore more on application because I may have many different identities, but I personally call myself mostly as inventor or engineer. The engineering is a science of solving problems, so I need to solve the real problem to make my things real. So I wanted to study a little more of translation applications. I take a look at it, and in early years, during my PhD, I explored mostly about software addition on engineering, solid, etc. Because that was the first thing that I did in my PhD, like including wearable devices and soft robots, which is very exploratory. So I have no idea it can be used, but it's very fun. But at a later stage, I take a little going into the biomedical devices as well, from the biomedical device coatings and some even UR probes that can be hybridized very well with the robustity to extend their longevity or functionality in a very sensitive brain tissues to make it more biocompatible. And even the one patent I wrote in MIT, like a hydrogen-elastomer hybrid probably, is being licensed by one company in the United States, like the computerized using reference systems like the FIRST. And it's now actually being used to manufacture to commercial ultrasound phantoms that are being actually used to train the clinical caretakers, etc. So it was really nice example and fascinating to see that with a very small amount of royalties every year. But still, around 3 years ago, I wanted to make the impact of what I study as a researcher being more broadened, especially in biomedical applications that might possibly even save people's life, which might be the ultimate cause that we can imagine about it. But the problem is, I don't know about this. So the only answer I can talk about is learn from clinical experts. Just ask them what can be done. This is what I do and what can be done. So I did it. I did it around 2.5 years ago. But before doing anything serious, I need to first ask one thing. I am good at wet adhesion, and whether it matters in biomedical application. And there can be a various way that it matters. But one thing that really catches my mind is a surgical sealing and repair, because it is a cornerstone of surgery. It is a major challenge in surgery still, because failure of doing so is inflicting tremendous clinical burden and economic cost. For example, gastrointestinal leak is one example. It's pretty common and it's costly and life-threatening, around 3 times increase in mortality once happened, but it's very easy to imagine why it's so bad. Something flowing in our gut or bowels or leaking in our belly, it's just a very nasty thing to imagine, so it's a really troublesome if it happens, but it happens because it's not fully solved yet. And the more easy to imagine example is bleeding, the major perioperative or traumatic hemorrhage or bleeding. It's quite common in major general surgeries, but it's always happening in traumatic injuries when something is broken down. It's very costly, and it's not surprisingly very life-threatening. This is the ranked first cause of death in military sectors, and second cause of mortality in civilian sectors, costing several millions of people every year in the worldwide. And more personally, I does experience what's happening with this. My brother is traumatically injured, and he has to hospitalize over 2 years, and I take care of it. I see all those problems of the surgical sealing repair. It's not only just the repair itself, but how things can go worse over time because the method to repair a thing is not appropriate. So it's real challenge. It's not only the real challenge in the real world, but it was a personal challenge. I really wanted to do something to better about this. But this is a big clinical problems, I have to understand better on the landscape of what's going on. And it has a long history. For example, sutures, which have a history of over 3,000 years, is standard care for surgical repair and sealing still now. And it is one of the first medical device that humankind ever invented. But it still has a lot of limitations and challenges. For example, the suturing is essentially a hand sewing process, and sometimes very complex procedure with the requirement of pretty nice surgical skills, and even more so for the complex geometry with the limited access to internal organs, etc. And in principle, it is like a needle piercing and fine processes of tissue damaging by nature. And essentially, it is a point-wise sealing, not a continuous sealing. So it cannot avoid the stress concentration around this noted point. And those stress concentrated point of this point-wise sealing is very susceptible against adhesions or local failures of leakage or the problems, or even more scar tissue formation or something bad things. So although it's a standard care and very old with history, it still has some limitation challenges that would better to be solved and addressed or remedied. And there are some more modern type of the tools, such as surgical stapler that invented around 100 years ago. But the use of stapler based on the literature is still not very much reducing the rate of surgical repair failure compared to sutures. So it's still not ideal. And even more so, there are some safety concerns as of the FDA issued a letter on safety concerns on surgical stapler around the last year, March. So it's still, there is ongoing problems. And the most recent approach to sort about, like talk about this issue is the tissue disease around 20 years ago. It is, in my opinion, conceptually more favorable because instead of using metallic needle to swing our tissues or metallic clips that are punching our tissues, having some nice glues that's spreading on top of the incision or injured tissues and let them be nicely, seamlessly, like close each other and heal each other, it's like conceptually more favorable. But the issue is this existing technology still fails to meet various clinical demands. And for that, I am not the person who can tell this. So I asked a lot of surgeons in interviews, over 30 people in near local hospitals with the help of our great mentors like Mass General, Brigham, and Baptist Roll, and Tufts, and even a little far away clinical ethics centers at the Mayo Clinic. That I learned a lot, and I summarized all they taught us and all they teach us for me. And there are repeating problems. They are complaining as oh. So first thing that they are complaining is a complex and lengthy preparation, because many of the existing products are really required to be thawed and mixed each other, or even shine some light, and etc. So these things are not very straightforward process, especially for the end users that are really working around the clock on a time-sensitive manners, which in very expensive work times. And also, many of them are not very compatible with the severely wet and bleeding tissues. So they actually need to clean up and dry the surface before applications. And slow sealing formation efficacy is one of the big things they complain a lot because it does not save the time. And it also really kind of makes things a little difficult to use in this intuitive manner. And lastly, the insufficient sealing strength and stabilities are really harming the confidence about the technology. So as an engineer, they are the voice of end users and customers. If I can solve all these things as engineering a solution, it might be a great thing to do. And I don't know whether we already solved all of this, but we can at least try based on what we did in the orders of validation. So to do that, we formed such a nice team, a collaborative team that is composed of a clinical expert, biomedical expert, and ourselves as a material scientist and engineer and mechanicians of the materials. So taking advantage of what we all did and the powerful and the amazing team that we could form around the MIT and some hospitals. So we first proposed the platform that we want to call it as a biodesic patch for sutureless sealing and the repair of the organs, which is simple and fast and non-tissue damaging and the fluid tight without, instead of being point-wise sealing. So what we wanted to envision here, so we wanted to make something like a duct tape. So we wanted to make a surgical duct tape that are bringing the convenience and the effectiveness of a duct tape into a surgical field or operating rooms based on a tough and wet adhesion thing that we have learned so much in my early part of the PhD and recently. And because they are implementing what we understand in terms of tough and wet adhesion, the tough and the fast wet adhesion, they are fast. It's working in just a few seconds. without waiting for many times or without using external devices. And because it imparted a tough bed adhesion, it shows a superior adhesion performance, at least doing better in commercially available tissue adhesives out there. And also it works for a variety of different tissues, so potentially helpful to make this more applicable across a different type of the tissues in different indications, etc. And the one thing is that the tough and the fast adhesion is a great thing, but when we demonstrate this to our surgical collaborators and clinicians, they actually worry about what happened if they misplace it. So we actually had to add additional novel chemistry to make it on-demand removable to allow that being okay to be easily removed without causing tissue damages by applying biocompatible triggering solution that we come up together with this detachment chemistries. So therefore, it now actually can be just to peel it off in just a few minutes and be reapplied if necessary, or removing something that people applied inside the body. So it becomes an extra upgrade. We actually didn't think about it initially, but we actually realized it is necessary later by hearing the end users' opinions. And as of the medical device that are aiming to be used as a surgical part of it, we actually need to work with the clinical expert to validate in vivo efficacy. As always, these things are going first in a small animal and the second in a large animal. And in this case, we choose the colon of the rat and pig. We made a very sizable defect. If it's not sealed, it may cause the bowel contents leakages and may cause a lot of troubles and may even make the animal dead. But we could actually seal without using sutures, and it could nicely seal without leakages, and they all survived and happily did it for a month, and we could find the defects are closed and healed very nicely. So we are very happy with it. And furthermore, on top of the open surgery with our great grad students, we wanted to expand the possibility of this opportunity or technology, not only in open surgery, but also emerging sectors of minimally invasive and potential robotic surgeries that using such a similar tools. So we come up with some nice designs and methodologies to converting these patches to be readily applicable for these emerging sectors of the surgery, not making a new tools, but based on existing tools, but making them compatible with each other. So it's now maybe more possibly applicable in more broader sectors, but we are still need to take a look at the very specific indication that we wanted on this particular minimally invasive sectors. And as implantable device or material, we need to really be careful about biocompatibility and degradability. So for the time sake, I may not go over the very details here, but we did a systematic in vitro cytotoxicity evaluation, in vivo histopathology, chemistry, and fluorescence, and even blood analysis of animals. So we are now confident that these are biosafe. Even the biosafety is a kind of comparable to that of a commercially available FDA-approved product. So we are happy to go over in more animal studies and eventually hopefully can be used in human, but they would need a more substantially well-documented procedures like following the ISO standard, but that is a little bit beyond the university laboratory. So we hope that we can do better in other entities. And we did the duct tape first and using first the two things that I studied. So what happened if I can use all three that I studied about with adhesion? So this is where I wanted to solve these hemostasis challenges. And stopping bleeding or hemostasis is a time-sensitive task, and it can kill people if not done properly. But the existing tissue adhesive cannot form an instant hemostasis because their mechanism is not fast, or they're relying on a slow mechanism such as diffusion and or formation of blood clots. So to remedy that, by using all things we know about adhesion, we propose a barnacle-inspired paste because we need to give some credit to the barnacle that give us the mechanism inspiration for instant hemostatic tissue sealing, which almost works as like a hemostatic super glues, and it combined everything we understand so far about wet adhesion. And this is how it works. Because we now incorporate all things we know about wet adhesion, it works on a foulant covered surface. Not only covered, it's actually actively coming out with the surface. This is a heparinized blood. And because it incorporates fast wet adhesion, it works fast in just a few second time scale. And because it incorporates the tough wet adhesion, its sealing is a robust, whose burst pressure is far exceeding that of the sutures or existing hemostatic agent. So it's really taking advantage of everything we know so far about wet adhesion. So I'm very happy to see this working in my bench. And again, as a medical devices, we need to check the efficacy with the clinical experts in vivo from the small animals such as rat in here. We choose the heart to show that it can actually deal with the high pressure bleeding. And also in large animal in here, we choose the heparinized pig liver to show that it can actually deal with the severe bleeding in irregular and deep wounds, partly thanks to its flowable nature that can nicely fill in and cover the already regular wound bed, which might be very difficult for like inflexible patch-like things or gauze-like things that in existing markets or technology. So we were very happy with the initial outcomes. And again, as the implants will mature, we need to talk about biocompatibility and essentially a wound healing after hemostasis. But I would like to, I will not go over the very details here. But if we did this comprehensive analysis in vivo pathology, immunohistochemistry, and fluorescence, even blood analysis, and we are kind of confident this is biosafe enough to try on animal, and hopefully for the human as well after we are like passing regulatory requirements to do about it. So far we talked about a surgical sealing and repair, and one last bit of what I did in biodiesel technology. Can we go beyond it? And what we thought about is biodiesel devices, because we are working with a variety of and like some medical device people like Professor Roche, our beautiful collaborators, is really always reminding us that people want to implant many things for therapeutic purposes or recording purposes, but when it comes to how people can apply these devices to internal bodies, especially wet organs, people still relying on a very old ways, like a physical attachment, which is nothing but just placing on top of it on slippery organs, or suturing it. But in my opinion, suturing is a little tricky because introducing tissue damages to suture to introduce extra devices to our body is a little not favorable. So can we do something on this conventional way of dealing with the devices being introduced to human body based on what we know and what we can do? So collaboratively, we kind of come up with a nice idea that, we can use what we know into biodiesel devices, we call, for long-term stability and functionality on wet dynamic tissues without causing tissue damages or unwanted instabilities. So probably can be a way that we can offer a promising way to literally seamless integration of these devices to human body. While this is pretty early stage development, so we still have very few proof of concept examples. For example, biodiesel drug depot and strain sensors. And we also try to adhere a biodiesel electrode by making it more conductive to get the signals like ACGs for a couple of weeks in living animals without causing troubles. But I think we have many things that are ongoing as a translation application with a real impact with a particular associated disease conditions. So we hope that we can show more in the coming years, but so far I can show only the proof of concept, but it's still very promising in my opinion. So with that, I need to conclude what I did, that I did 3 quests. Although sadly, I really sad that I cannot show the second and third one due to the time sake, which is around half of my PhD. But hopefully throughout my PhD, I did something that being helpful for the people that are working in this field to making these 2 different worlds are being a little better interfaced or better working with help of hydrogel technologies, while there are a lot of things to be done. Fundamental studies about how hydrogel and tissue at the interface level need a lot more study. Translation effort in close collaboration with clinical expert is essential before its true use in human. Scalable and reproducible broad dissemination is essential because sadly so many papers are not reproducible, but we should not do that. And finally, the commercialization and being eventually off-the-shelf technology, not only being used in a few number of research groups and collaborators, but has been used by the general public and experts that can freely buy it and use for to treat actual problems would be the ultimate goal. But it may take time to see that, but I just wish to do that in over time. And as the one really last bit, I want to summarize my PhD journey in numbers, and including today, exactly 2,300 days I spent in MIT. And throughout my PhD, I published 20 first authors and 30 co-author papers in total. And interestingly, my first author paper attracted more than 3,000 citations, so it's kind of a little product, like a popular. And I attended 20 conferences, and I had 30 beautiful internal and external major collaborators. And I had more than 30 surgeons interviews to learn, which is great opportunities. And I had the luxury of my first author papers being covered 11 times by MIT News articles, so that if I could reach a lot of general public beyond my academic colleagues. So with that, I would like to acknowledge the funding support. They always need to be acknowledged the very first, but without which I cannot do all these complicated things. And my mentorships and academic support from Professor Hyunwoo Yuk as advisor, and Professor Christopher Knapsey in the Mayo Clinic for clinical part of it, and administrative support from Christina and Leslie, without which probably any dollar would be properly spent, and group members and collaborators. And there were some relaxing moments from rabbits that I had. The Amy was passed away in 2015, and local rabbits afterward I rely on is in Cambridge. And finally, my families that always been the greatest motivation, inspiration on everything that I do, including the research work. And with that, I'd like to thank you so much for your time and attention, and hope it is enjoyable and informative in these snowy days in Boston.
Wonderful. Questions from the audience? So everyone, including the faculty members, can ask questions now. And then after this public Q&A, we'll move to breakout rooms for a private Q&A session. Any questions?
Oh, no question?
From Professor Shin, great work, Hyunwoo. Any question?
Can I ask one?
Oh, sure. Sure.
Yeah, so very nice work, and as Professor Zhao mentioned, many group members, including myself, got a lot of help from Hyunwoo when we started our graduate studies. So that's very what I feel grateful for him. So bioadhesives are I guess made of biopolymers, and does that mean they're meant to get degraded eventually after a certain period of time?
Yes. Well, actually, that's the hard part. And it's actually necessary because when we take a look at all the existing technologies to deal with these surgical sealings and repairs, such as sutures and etc., many of them are actually degradable because people or the surgeons don't want a readmission surgery just to remove it, especially if it is not a skin, it is internal organ. Opening up the body or doing complex surgery just to remove something after everything is done is not very favorable. So it shouldn't be degradable. So the current ones are degradable, at least when we check with the animal studies, at least the small animal levels. But I believe there are much more work to be done to fully optimize what is the degradation profile and how they are actually competing with their purported purpose of supporting a mechanical support as a sealing. It's really a more complex problem. So it's essentially degradable material, and many of the hydrogel polymers are degradable by hydrolysis or enzymatic degradation. While I think it's a lot more to be done in terms of a little more larger scale studies, etc. But I think that's the essential criteria that would be eventually need to be met for bioadhesive, because I think it is unrealistic that someone need to do a readmission surgery to remove the bioadhesive after the repair.
All right, great. Thank you.
Hi, can I ask you a question? How are you? This is Zheng Wei from McGill University.
Sure.
Hi, so this is Zheng Wei Ma. I'm working with Professor Chen-Yu Li, his PhD student. So as you might know, we're also actively working on the field of tissue adhesive, and hopefully eventually we can bring them to the clinics one day. So I guess other people are intimidated and impressed by your work, me included. I'm a big fan of you and Professor Zhao's work. So I guess my question is about more far-fetched vision. I was wondering if you can share a vision about the technology or how engineering can address the problems with chronic diseases. For example, a lot of disease that for patients with those kind of deficiencies regarding their regenerative capability. I think your technologies are excellent tools to for like for those traumatic incidents, because as you mentioned, a lot of limitations of current technologies, and also the limitation of human beings. The blood clotting is very slow, and also regeneration is very slow. So how do you think that we can, as engineers, can address these problems with hydrogel technologies? How do you envision one day that we can truly bring human and machine together? Thank you so much.
Well, that's a great question. I actually need to answer in this way. I think we are not yet close to solve any of it. We need to work a lot more. And the one thing, like my early part of the PhD is actually nothing to do with the biomedical or clinical things, but later I learned more about it. And the one big lesson while doing so is, I think it's better not to be not to be exaggeratively optimistic, but being very patient and being persistent about doing things. So for chronic disease conditions, I believe there are certain type of chronic diseases or chronic conditions that we can even already try to solve using existing technology. For example, some chronic wounds, we are also having other projects working on it. But for, I think that requires more collaboration with the clinical experts and especially tissue engineering and biologists who understand the problem, because the reason that I put as the first, as the things need to be done is how this hydrogel tissue interaction would go, especially in the context of a hydrogel adhesive, is that we don't know. People don't know very well, because including myself work and other people's work, we're still fully focusing on mostly about acute efficacy of these adhesive things. But we need to learn better that how these things are actually working on over time. And even for non-diseased, like well-healing tissue, we don't understand very well. But I believe it will require a little more accumulation of knowledge to talk about pathologically problematic chronic diseases to be solved. But as academic people, I think it's a great thing to have, because if there is no challenge, we lose our jobs. So I think it's a great thing. There are a lot of challenges, and we can spend decades to solve it. And eventually, I believe will be solved, but not sure how fast it can be.
Thank you so much.
Can I ask one question?
Sure.
Yeah. Thanks for the amazing presentation, Hyunwoo. So in your e-adhesive work, I think it is quite tricky to synthesize and make the materials with a good adhesive and electrical property at the same time. So I'm wondering how you achieve it. And my second question is, please answer about the first question.
Please complete the question so that I can answer together. What was the second question?
My second question is, though you serve so many of them, what do you think is still the remaining mission in the adhesive hydrogel field?
Yeah, for the first question, it's a work collaborated, like actually led by our beautiful postdoc Juan, and we actually spent a lot of time to make this balance. And it is true that the material is actually not very straightforward to synthesize. So it actually worked after so many trial and errors. And the one thing that we keep doing as a follow work or new work is initially, as you can see from the presentation, we focus first a lot on a mechanism, which can be generally applicable regardless of specific choice of material. So, but once that thing being done, and I think that what we did in the wet adhesion is actually this mechanistic understanding on general design principle, we can take advantage regardless of specific choice of the material. But I think we passed that stage, at least in our side of it. So what we are now doing as next step is we need to now focusing on a little material play that still implementing these mechanisms, but make the material more reproducible, easily disseminable, and is actually being useful, or considering all the requirements like the biocompatibility, degradability, and all this easiness and fabrication, etc. So that achieving what we showed as a proof of concept by incorporating the same design principles and mechanism, but make it more easy to use for the other people beyond our groups or collaborators. So that's exactly what we are doing. So I believe the ongoing work that we do as a follow work of that e-bioadhesive would provide a much better material that doing exactly the same thing or even better job, but with a much simpler manufacturing, fabrication, and preparation that eventually we want the people can be easily used. So I think we are now transitioning from this mechanistic view as a mechanical engineer to the materialistic view that is a little more toward dissemination of the technology, which we are doing. And the next stage would be commercialization. We want this to be actually being used so that we need to pass a lot of regulatory hurdles. And I don't know how long it will take, but I believe there are some stages of development. And in my PhD, I passed around the mechanistic part of it. And I'm currently actively working on the materialistic part of it with collaborations. And with that thing being almost done, I believe we will transit into a translation stage with the commercialization focus.
Bing Ying, do you want to ask a question or I can repeat? So Bing Ying asked a question in the chat room. It's about the point of care capability of your hydrogel adhesive, as now your material need a certain storage condition. Hyunwoo, can you comment on that? The storage condition.
That's a great question. So again, I think OEB does care about a storage condition because I don't want to make a sample every time before I need to do experiments. So it's storable in like a desiccated condition with the desiccants for weeks or even months. So that actually can be easily storable. But I think we will think more when we are going more on the translational pathways. But I think currently we can store that well as long as we can keep it against the moisture for this dry adhesive series. And some other technologies will require specific considerations. So it's storable yet, but I don't know whether what we choose now is the ultimate optimal thing that we may use, because this storage and circulation of the product, etc., is not oftentimes like a consideration can be best discussed or considered within academic boundaries. So we will probably learn more about industrial engineers who are very much expertise in the packaging and the circulation of products. So currently it's storable, in my opinion. It works very well over a few weeks and even months. But I think it will become better as we learn more about things from industry. And in some sense, I think that's one thing that the academic field as a whole should probably going forward. Like we can learn from industry, even in our academic projects. But it's storable, but I don't know whether what we choose now as a solution will be keep using, because we may likely learn a better solution than that from the industrial engineers.
Any further questions?
I have a question. First of all, really excellent work as always, and your presentation style was great, and I know your work is really solid. I have a question, which is, if you could do your PhD all over again, like what would you have done differently? Or if you had more time, which of these things that you worked on would you want to pursue more? Like if you were to continue, if you had, I guess, more time, like which was the most interesting?
First of all, I probably don't want to do a PhD again. But if I can do, I will just let it flow. I think one big lesson after living a crowded PhD life, it's a wisdom of not having expectation. I'll just let things flow again, and I will just make the best option and best choices in each step, and probably will be exciting in different manner. So I don't have a particular thing that I love to repeat if I have another chance. But one thing that I really likely do if I have a chance to do it again is, as Professor Zhao mentioned initially, I have some personal causes that I want to solve. And I'm still strongly believe the fact that the most personal problem is the best problem that I can solve. So I am not sure what kind of life I'm going to live again if I have another chance, but I think I will try to solve the problem that is resonating with me the most. Then I probably will do a great job. For example, I have nothing to do with the bioelectronics before, although I have some beautiful collaborators that can introduce me about it. But the reason that I really kind of obsessed with that topic and wanted to do something better is the fact that my little brother doesn't sense his right fit because he has a peripheral nerve injuries and spinal cord injuries. And after certain years ago, my mother got a Parkinson's disease. So I now have a neurological disease and degenerative disease in my table or bowel problems. So it really pushed me, nudged me a lot to study more on that thing because I should learn more. I should work on something if I want to do something to contribute for addressing or solving all these problems that I am personally suffering. So I think I will do the same thing if I have the same problem. But if I had a different set of problems, like cancer in my family, I believe I am not even in mechanical engineering. I'd probably go for biological department to study cancer.
I see. Thanks. That's a cool response.